In this video, we solve problem 15.2.038 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the work done by the force field F, on a particle moving along the given path. And we're given this as our field, and we're given this as our path. This is really nice because the parameterization is already given to us. We know where we start, we know where we stop, we know that we're on this path, and we have this field right here. Now, I prefer to write this in component form. This is a field in the xy plane with components x squared and negative y squared. And remember, the work done is going to be the line integral over f of f dotted with that displacement vector. And that displacement vector is really just the velocity times dt. So eventually we're going to integrate this from one t value to another. And then we need to write this field in terms of t and dr in terms of t. Now the field can be written in terms of t by replacing x with x of t, where x of t is right here, it's that cosine cubed, y with y of t, where y is that sine squared t, and then we'll dot it with r prime of t, and then multiply by dt, and that's where r of t is the vector valued function with components x equals cosine cubed t and y equals sine cubed t. And we want to start here and end here. So we need to think about the values of t that will give us this xy location and then this xy location. So we know this is our start point, x equals 1, y equals 0. And our ending point is over here. Now my x value would be 1 for many values of t, but one that will work is t equals 0. When t equals 0, cosine of 0 is 1, so cosine of 0 cubed is also 1. And when t equals 0, sine of t is 0, so sine cubed would be 0. So when t equals 0, we could be at this location here. Now the way we want to think about it is that as t increases, we're tracing out this curve. So I want to pick a value of t that's larger than 0 that will get me over here to this location. And I actually want it to be the very next time that component function for y is equal to 0. Or excuse me, the component function x of t equals cosine cubed t is equal to 0. And the reason is this. X is starting at 1 and then it's going back to 0. And it's only doing that once. It's not sort of repeatedly going back and forth over a path or going over different points. It's not continuing like that. So I want the next value of t that I could substitute in here so that this function would be 0. And if you're saying, why is it 0? It's because at this location, our endpoint x is equal to 0 and y is equal to 1, as stated right there. Maybe I should write it out. So for our starting point, we said this. We want x of t, which is cosine cubed t, and y of t, which is sine cubed t, to be equal to 1, 0. So that means we want a value for t that will cause this system of equations to be satisfied. The x value needs to be 1. While at the same time, the y value is 0. And because we know how cosine and sine behave, because we know that our sine function in the xy plane, y equals sine of t looks like this, and our cosine function in the xy plane, that looks like that. We know that when t is equal to 0, that would be right here, cosine is equal to 1 and sine is equal to 0. So there are many times that happens, but we just want one time. And so we'll say time t equals 0 is associated with that start point. And then similarly, we want to find the end point by setting our x of t, y of t, equal to the coordinates of that end point, which is 0, 1, or you can look at the graph and see it's x equals 0, y equals 1. And again, that leads to the system of equations, x of t, which is cosine cubed t. I want a t value where that is 0. And y of t is sine cubed t. And I want a t value where that is 1. And I think we can see that the next time that cosine would be 0 is right here. This graph is not to scale, but that occurs at t equals pi over 2. And when t equals pi over 2, at the same time, sine is equal to 1. So cosine is 0 at t equals pi over 2, and sine is 1 at t equals pi over 2. So when we cube them, 0 cubed is 0, 1 cubed is 1. So that is a solution to this system of equations. Okay, so that is one way that we can evaluate this line integral. We'll evaluate the integral from a to b of the field in terms of t. So it's actually a function of x and y, but if we were a little particle traveling along this path, we'd be experiencing different forces at different times. And that force at a certain time t would be given by this. And then we would want to dot that with the velocity of that particle traveling along the path. That dotted with that times dt is going to give us work on a little tiny piece, and then we'll add those up for all the pieces. So that's a possibility. Now, we might be very fortunate and have a conservative field. So we should always check and see if our field is conservative before we just evaluate the line integral, because if the field is conservative, then we have options. If the field is not conservative, we're stuck. We have to do this. But maybe the field is conservative and we don't have to do that. We might be able to do something else instead. So here's my field. It's in the plane, and in our class, we've been labeling the first function m of x and y and the second function n of x and y. Now remember, the test for conservative fields is that the partial of the x component with respect to y has to equal the partial derivative of the y component with respect to x. So let's do this. The partial derivative of m with respect to y is 0. Okay. The partial derivative of n with respect to x. There's a constant times x there. The derivative of a constant times x is that constant. And we're treating y as a constant. And those are not the same. So since those two partial derivatives are not the same, the field is not conservative. And we have to evaluate the line integral directly. But it's really not that bad because they already gave us the parameterization. We were able to infer t equals 0 and t equals pi over 2 from the starting point and ending point that they gave us. So all we have to do now that we know that this is 0 and that's pi over 2, is find the field in terms of t and find r prime of t. You can do that in any order that you want. So here's my field. In terms of x and y, it's x squared times I hat minus xy times j hat. Now I want that in terms of x of t and y of t. I'm just opening up some parentheses to substitute in my x and y. Remember, x of t was cosine cubed t, y of t was sine cubed t. So my x component of my field is x squared. So I'm going to substitute in this function of t right there. And my y component was negative x times y. I'll substitute that in here as well. And you can think of that as a power raised to a power. It is. It looks a little different because you're dealing with trig functions. But if I have a power raised to a power, I can just multiply those two exponents together. The same is true here. If I have cosine cubed t and I square it, I'm just going to multiply the 3 and the 2. That turns out to be cosine to the 6th of t. And then over here, there are actually a couple of options that you have. We could keep this in this form. It's really up to us. I think I'll leave it in this form for right now, and I'll put the sine function first. Okay, so that gets us f in terms of t. Now, once we have f in terms of t, we need to compute r prime, and then we'll take the dot product. Now, r may need to be rewritten first, just to make it a little bit easier to take that derivative. Cosine cubed t is cosine of t, quantity cubed. And sine cubed t is sine of t, quantity cubed. When I write it in that form, it's even more obvious that I need to use the chain rule when I take the derivative of the x component and the y component. So I will do that for my x component. The inside function is the cosine of t, and we're cubing it. For my y component, the inside function is the sine of t, and we're cubing it. When we take the derivative, we'll take the derivative of the outside first. And of course, we take derivatives component by component with vector valued functions, as we discussed in Unit 2. The derivative of the outside function, or the derivative of a function cubed, is 3 times that function squared. You put the inside function back in, don't do anything to it yet. And then you multiply by the derivative of the inside. The derivative of cosine of t is negative sine of t. So that's my x component of r prime. The y component is actually very similar. I've got a function cubed. The derivative of a function cubed is that function squared, or excuse me, 3 times that function squared. So we bring the power down, we multiply by the function to the 1 less power, put the inside function back inside, and multiply by the derivative of the inside. Okay, now we've got f and we've got r prime, and we want to compute the dot product of those two now. That'll be our integrand. We're going to take the x component of our field and multiply it by the x component of r prime. So I've got 6 cosines there times 2 more. That's going to be 8 cosines times a negative 3 sine of t. So I'll write that this way. Cosine of t to the 8th times negative 3 sine of t. And then remember, if we take a dot product, you're adding that the result of a dot product should never be a vector. It's this times this plus this times this. If you get a vector, then you know you didn't take the dot product correctly. You're always supposed to multiply and add, and keep going until you run out of components. And we're going to do the same thing here. Now we've got a 3 and a negative 1. So I can think of that as a coefficient of negative 3. Could have written minus 3, but that's okay. I already wrote the plus sign down. And then I've got 3 sine functions here and 2 more. So that's going to be 5 of those. So I'll have sine of t raised to the 5th. And then I've got cosine cubed times another cosine. So it's going to be a cosine of t raised to the 4th. And I know we could write that differently with the powers on the names of the trig functions, but I'm choosing to write that like that for right now. The only reason I chose that way was because I thought that it might be easier to integrate if I leave it in this unsimplified form. But after I've taken my dot product, now I can examine it again and think about whether or not it can be simplified and if that's something that I want to do, because remember, we're preparing to integrate. We need to write this in a form that we can take the antiderivative of. Now I notice right away, we can factor out a lot here. Both of these expressions, this one and this one, these two that are added together, we can think of them as groups. We can group them that way. They both have a negative 3 in common. They both have 4 cosines in common, and they both have 1 sine in common. So I could factor out that negative 3 cosine of t to the 4th times sine of t. And then just ask myself, okay, this times what will give me this first expression? The only thing that's missing is the other 4 cosines, because there are 8 of them there. I've got 4 here. So what would be left over here is cosine of t to the 4th. And then over here, I'd ask myself, okay, if I factor out the cosine of t to the 4th and the negative 3 and one of the sines, how many, or what is left? And what's left is the 4 sines remaining. If I take out 1 sine, there used to be 5. Now there are 4. Okay. Now, when I look at this, oops, I noticed just a second ago, this times this gives me this, but then I need to add this term over here. This times this gives me the second term, but we're adding those. Distribute over addition and we get that. Okay, so we're good. One thing I noticed though is I have a factor of sine of t. Since I have a factor of sine of t, if I want to integrate this, it'd probably be best to integrate it with a u-substitution where u is a function that has a derivative of sine of t. So that means our u should, or a constant times sine of t potentially. And that means our derivative should involve a cosine, or excuse me, our u should involve a cosine. Oops, that's the plan. So I've got the integral from t equals 0 to t equals pi over 2 of f written in terms of t dotted with r prime. And that's this. Now, because I'm going to do the u sub where u is equal to cosine of t, I'm going to factor that sine of t off to the far right and put everything else in brackets. So I've got -3 cosine of t to the 4th, and then I'm grouping cosine of t to the 4th plus sine to the 4th, or sine of t to the 4th. So that quantity is multiplied by that quantity, and all of those guys are multiplied together. And then all of that is multiplied by that one sine of t that I haven't accounted for that and that. And of course, that's times dt. So I'm saving that for my du, and I'm letting u equal cosine of t. Well, if u is cosine of t, du is negative sine of t dt. And I actually have a negative and a sine of t dt. So I think I'll bring that negative out there. So that's just a du. And then this would be a u to the 4th. Because cosine is our u. This would also be a u to the 4th. And sine of t to the 4th needs to be rewritten so that it needs to be rewritten in terms of my cosine of t. That can be done pretty easily just using one of our Pythagorean identities. We know that sine squared of an angle plus cosine squared of the same angle is 1. And with that in mind, I can solve for sine squared of that angle. And sine to the 4th is sine squared squared, or you can think of it as sine squared times sine squared, whichever you prefer. But I know that I'm going to end up with 1 minus cosine squared times 1 minus cosine squared, or 1 minus cosine squared quantity squared. I'm going to think of it that second way. It's really up to you how you think about it. Either one would be fine. You just do it what's more comfortable for you. So I'm saying that that is sine squared, and that is 1 minus cosine of, or cosine squared t. So I've got 1 minus cosine squared t, and I'm squaring it there. And remember, cosine of t is our u, so that's going to be a 1 minus u squared, quantity squared. Okay, so let me rewrite this, and then we'll do our u substitution. It's pretty much done. I'll take that negative and put it out there with the sign. Oops. I said that and then I did not write the right thing. So I had cosine to the 4th of t there. And then I've got cosine to the 4th of t there. And this we're thinking of as 1 minus cosine squared t squared. Okay, so that's all in terms of cosine. And I've got the negative sine of t dt as my factor off to the far right. Okay, well, if u is equal to cosine, du is negative sine of t dt. This is u to the 4th. This is 1 minus u squared, quantity squared. We're taking all of that and we're multiplying by 3 times u to the 4th. So in terms of u, that becomes 3u to the 4th times the quantity u to the fourth plus this squared. If you write that twice in FOIL, you'll get 1 minus 2u squared plus u to the fourth. That can be something that you memorize, a minus b quantity squared, or you can write it twice in FOIL and you'll see that outer times outer and inner times inner term add together to give us that. So that's all of that. And then that's just a du. And I know I need bounds. We'll add those in just a moment. Now I've got a u to the fourth times a u to the fourth. That's 2u to the fourth minus 2u squared plus 1. Not too bad at all. And we'll distribute. You can take out that 3 if you want to. Distribute the u to the fourth. And we'll have 2u to the eighth minus 2u to the sixth plus u to the fourth du. Okay, now we need new bounds. To find the bounds for u, and they have to be bounds for u because these integrals are in terms of u, we have to take the bounds for t, which were t equals 0 and t equals pi over 2, and substitute those into this function. U of pi over 2, that's our upper bound, is cosine of pi over 2, which is 0. So the upper bound maps to the upper bound. So we'll get a 0 there. And then when t equals 0, we get cosine of 0, which is 1. So you've got a 0 and a 1 there. And a 0 and a 1 here. Now you can flip those and multiply by a negative if you want to. It's up to you. You don't have to. Okay. Now from here, I'm just going to leave it alone. We'll just use the power rule to take our antiderivative. Bring your 2 down, add 1 to the exponent and divide by the new exponent. Bring the negative 2 down, add 1 to the exponent and divide by the new exponent. Then there's no coefficient to bring down here, but we'll add 1 to the exponent and divide by the new exponent. Substitute in 0 and 1 and subtract. At 0 for u, we're just going to get 0. Then at 1, we'll have 3 times 2/9 minus 2 over 7 plus 1 over 5. And then we'll multiply by negative 3. And I did that arithmetic on my calculator. I got negative 43 over 105. So it's really not too bad. We did have to refresh the trig integrals techniques and remember what that is. Basically, that was what I did right here. When I looked at this and I factored out what these two had in common and I saw the sign of t, I said, okay, I can do a u sub here where u equals cosine because I've got a sine of t for my du. Now, if you choose to just look at these two forms separately, that would be just fine as well. Remember what we said in our trig integrals section. If the power of sine is odd and positive, save a sign for du and let cosine equal your u, because then you can do the u sub for that, where du would have that sine of t as a factor. And then this is very similar. If you've got the sign of t is raised to an odd positive power, save one of those signs for du, write everything else in terms of cosine, which is what we eventually did, and then let u equal cosine of t. So we had to do a little bit of that, and we had to use our parameterization and our starting point and ending point to infer the values of t. But once we did, it's very straightforward. You just write your field in terms of t by making a substitution. You write down your r of t, substituting in your x component and y component, which are given from the parameterization of c. Take its derivative, component by component, take a dot product and integrate. And it's pretty straightforward from there. I hope that helps. Let me know if you have any questions.